Hey everyone, we're starting proofs today. Just want to kind of go over some postulates before we start. Then we'll get into writing simpler proofs called flow proofs and a paragraph proof. Um, I just kind of want to go over some stuff, make sure we know where we are, and then tomorrow we'll get into the full-on two-column proofs that are the backbone of what geometry proofs look like. So let's get started. Postulates, they're sometimes called axioms, but a postulate is basically a statement that is accepted as true without any proof. You're told it exists, you're told that it's true, and from there on out, you know it's a fact, it's truth. Um, there's really no questioning what you've been told. It's many of the basic principles of geometry that we learned last chapter. Um, is what we're going to be kind of going over again as the postulates that form the basis of our geometry stuff going forward. So postulate one, through any 2 points, there is exactly one line. We learned this before. You learned it from algebra that whenever you were trying to graph the y equals mx plus b, so you're trying to graph the equation of a line, you needed to plot at least 2 points. Once you had the 2 points plotted, then you were able to connect the dots and create your line because the line had to go through 2 points. Postulate 2.2 talks about planes, and it's through any three non-collinear points. The points have to be non-collinear to be a plane. There's exactly one plane. There can't be any more than one. There can't be two. There can't be three. It has to be one. Just one plane for three non-collinear points. We get to postulate 2.3. Now we're talking that a line contains at least 2 points. You may recognize this as the converse of postulate 2.1. 2.1 says you need at least 2 points to create a line. 2.3 says a line contains at least 2 points. So if you try to convert them both into if-then statements, you're looking at the converse. Same thing with postulate 2.4. It's the converse of postulate 2.2. A plane contains at least three non-collinear points. You can have 4, 5, 7, 9 million, infinite amount, which is what it is. It needs to have at least three non-collinear points before you can start calling it a plane. Postulate 2.5 tells us that if 2 points lie on a plane, then the entire line containing those points is in that exact same plane. Remember, you need 2 points to create a line. So if the 2 points are in a line, that line is going to be on a plane, and then that plane is going to go on forever. The line is going to go on forever. So as long as you have 2 points in the plane, the entire line containing those points is in that exact same plane. Postulate 2.6 tells us if two lines intersect, then their intersection is exactly 1 point. We learned this last unit that lines intersect at 1 point. If they intersected at multiple points, then you're probably looking at it being the same line. We know the lines are straight, they can't turn, so there's no way that the line could ever intersect at more than 1 point. And then postulate 2.7, the last one we're going to talk about today, is that if two planes intersect, their intersection is a line. What that's telling us is if you think of the planes being the walls of a room, the walls meet in the corner. That corner is a line. So if the intersection is a line when the plane crosses. It's not a point. It's not a line segment, or it could be a line segment if it's a picture, but it's definitely a line because the planes and the lines go on infinitely in either direction. So intersections of a plane is a line, and then you can have more than two planes intersecting at that point. So there's an infinite amount of planes that can intersect on a line. That make sense? Okay. We're going to move on. The postulates, like I said, they're the basic structure we will use to complete our proofs going forward. We need true statements when we're doing proofs to prove something is valid. So we have to have a true statement to kind of justify what we're saying as we're trying to do our proof. So we're going to use the photo here in the right to explain why each statement's true, and then we're actually going to talk about the postulate we used. The picture is much clearer in the book if you want to take a look at that. But what we're looking at is lines N and P intersect at point D, and points A and B and D form a plane. So take a few minutes to kind of look at it, judge what you want to do. We're going to have you type out an answer before you move on, and then we'll go over the answers in a few minutes. Okay, so lines N and P intersect at point D. We kind of look at our stuff. I'll use the cursor to kind of point it out. Line N is this green line that comes over on the left side of the top part of the building. Line P is this other green line, kind of goes the other top of the building. They intersect on the corner of the building, so they're intersecting at one point. So we see that the top edge of the buildings are represented by the lines. The lines intersect at the corner with D, and then postulate 2.6 tells us that two lines intersect at exactly one point. That's the postulate you would use to kind of say that that statement is true. Points A, B, and D form a plane. So again, we look at points A and B. They're on this pink line to the left of the building. A and D is the top line, line N again. So they're points. There are 3 points. The points are all non-collinear. Yes, A and B are on the same line. A and D are on the same line, but the three of them together are on different lines, so they're non-collinear. So that tells us that we have a plane. Postulate 2.2 tells us that 3 non-collinear points make a plane. We have our 3 non-collinear points. We have a plane. If you think of it, it's the face of a building, so it's a flat side of a building. It represents a plane. Does that make sense? Okay. Because the postulates are true, we're always going to be able to use them to determine whether statements are true, always true, or never true. They may be sometimes, they may be never, maybe always. We can use the postulates to determine and decide, are these statements true or not? So here are some examples. If two coplanar lines intersect, then the point of intersection lies on the same plane as the two lines. So when we think of it, we have two lines. We've been told that if there's a line, all those points are on the same plane. So we have two coplanar lines. So the two lines are both in the same plane. And now because they're two distinct lines, we can definitely say that there are more than 3 points. So there's a coplanar point, but then our lines are going to intersect at one point that has to be on that same plane because the lines are coplanar. So that's where we're getting that it's always true. There's never going to be any instance where two coplanar lines are going to intersect and that intersection point is not on the plane. So you'd use state postulate 2.5 to justify that. The second example is 4 points are non-collinear. Is this true, sometimes true, always true, or never true? Sorry. When we think of it, we've been told we only need 2 points to create a line. So we're definitely looking at postulate 2.3. It's 2.3 more than 2.1 because we're told that there are 4 points and we need at least 2 points to create the line. What we're looking at, though, is this statement is sometimes true because you might have the line where only 2 of the 4 points are non-collinear. It's asking if there are 4 points are non-collinear, so so we could end up having a line that has 4 points on it. So we can't say all the time, yes, that it's a true statement. Sometimes it's going to be true, sometimes it's not. Does that make sense? Okay. Moving on, it's your turn. Take a few minutes, take a look at these 4 examples. State whether they're always, sometimes, or never true. Explain your answer. If you just want to list what postulate you used, that's fine. If you want to give me an explanation, again, that's fine as well. Just try to give me some indication that you know what you're talking about and you understand why everything is the way it is. Okay, the first one. There's exactly one plane that contains points A, B, and C. Again, we've been told multiple times that we need 3 points to form a plane. So we have 3 points. It tells us that yes, they might be on a plane. The problem is if those 3 points are coplanar, now they're on more than one plane. Because remember we said that planes intersect at a line. So if the lines are coplanar, there's an infinite amount of planes that could be crossing at that point, at that line. So it's not just going to be one plane that contains the points in exactly one plane. There are multiple, more than one, actually an infinite amount of planes that intersect at a line. So if the points are collinear, then there's multiple planes, not just one. The second one, points E and F are contained in exactly one line. Again, we're told in postulate 2.1 and postulate 2.3 that you need 2 points to have a line. So you could have used either or, but this is always going to be true. 2 points forms one line. One line for 2 points. Number 3, 2 intersecting lines determine a plane. here we got to think about it. So is this true? Is it not? Maybe it's true. Sometimes it's true. We had a problem earlier. We looked at that there were two coplanar intersecting lines, that the intersecting point was in the same plane. So, okay, that kind of helps us with this. That's true on that point. But then when you start to think about it, two intersecting lines, if we're talking about them determining a plane, if we have one line has 2 points, we have another line intersecting that also has 2 points. Well, now we're actually able to say that we're dealing with at least 4 potential points on the plane. We only need 3, so this is always going to be true. Two intersecting lines are always going to form a plane because we only need 3. And when you think of it, they intersect at 1 point. Each line then has an additional point because you need 2 points to create the line. So we have our 3 points that are non-collinear because they're on 2 different lines that create our plane. Excuse me. And the last one, planes R and S intersect at point P. We talked about it in example 1 that planes actually intersect at lines, not at points. So then this is never going to be true. Postulate 2.7 states that when planes intersect, the intersection forms a line. So never are planes going to intersect at a point. Does that make sense? Because once you kind of understand how the postulates work, then we can use them to start doing our proofs. Okay, proofs, like we said. Proofs are used to prove a conjecture with deductive reasoning. To prove a conjecture, deductive reasoning is used to move from the hypothesis to the conclusion of the conjecture you are trying to prove. In our proofs examples, the proof's a logical argument in which each statement is made as supported by a statement that is accepted as true. So we're going to use postulates to do our proofs. But when we think about it, we're going to have a given statement. You're going to have to say, given this, prove that. So our given statement is going to be our hypothesis. And then the conclusion is what we're trying to prove. That's the conjecture that we're trying to prove, like it says. So we're trying to get from point A to point B. We're going to be using our postulates and some theorems we'll talk about tomorrow. We'll mention it briefly today, but it's more going to be dealt with tomorrow, that you can use the theorems to kind of help you make the proofs work as well. So the first type of proof we're going to talk about are flow proofs. A flow proof uses statements. It's basically like a flow chart. So we're going to put our statements in a box, and then we're going to draw an arrow from the box to the next logical progression of our argument. And then each reason for our movement is going to be written underneath the box. You'll see it in the example. But the steps to write the flow proof are, we're going to start with write the given statement in a box with the word given underneath it. So if you're told given triangle ABC is a right triangle, then your given is going to be triangle ABC is a right triangle in a box. Underneath that, it'll say given with an arrow coming off that to the next logical statement. Then the second step is kind of going through and creating our deductive arguments for each chain of events in the statements. So we'll be working with algebraic proofs in this unit. So you're going to kind of think of what's the next step to solve my equation, which is what we're trying to do with an algebraic proof, is you're solving an equation to prove the answer, given reasons why we're able to get to that proof, get to that final answer with the properties that we talk about. And then everything's linked together with arrows in the statements. And then your last part is just state what it is that you've proved. So we've gone through, we've done all the proof. Our last box is going to say proved what we proved in the last box, and then the reason we were able to get to that point. Told you, I mentioned, we're going to be working with algebraic proofs. So we're going to kind of brush up on a couple of the properties that we're going to need to do our algebraic flow proof on the next example. You'll have a couple to do on the homework tonight. And then from there, we'll kind of work through with a couple more as we kind of go through the unit just to kind of see how it works with the 2-column proofs and stuff. But we're just brushing up on some of the properties. So you have your addition property. If A equals B, then obviously A plus C is going to equal B plus C. The subtraction property is the opposite of that. If A equals B, then A minus C is going to equal B minus C. Your multiplication property, if A equals B, A times C is going to equal B times C. Again, the division property is the opposite of that. If A equals B and C does not equal 0, that's important. Then A divided by C is going to equal B divided by C. What they call a reflexive property we're actually going to use in geometry a lot is A equals A. So something's always going to equal itself. The symmetric property of equality is if A equals B, then B is going to equal A. What this kind of does, if you go through and solve an equation and you end up with X on the right rather than on the left when you're solving the equation, you can flip it because just because one equals X, then X is also going to equal 1. Our transitive property, if A equals B and B equals C, then A equals C. We're able to say that. That's the transitive property. Our substitution property is that if A equals B, then A is able to be replaced by B anywhere in the equation or the expression. Think of that when you went through and you solved that X equals 1. You're able to then take that 1 and plug it back in wherever you see X in the proof to prove that your answer was right. And the last one everybody knows is the distributive property, that A times in parentheses B plus C equals A times B plus A times C. That's probably the most well-known property in algebra. So like I say, when we're writing an algebraic proof, it's like solving the equation and then we're just telling every step of what we did. So our example is, prove that if y plus 2 divided by 3 equals 3, then y equals 7. So we go back to our steps. We begin by stating what is given and what you are trying to prove. So we're given y plus 2 divided by 3 equals 3. That's what we're told. We're trying to prove y equals 7. So our first step of our flow proof is to give our given in a box. So y plus 2 divided by 3 equals 3. That's our given. So that's what the first step of the flow proof looks like. We draw our arrow, then we bring down the second part, which we're trying to do. What's the next step to get through to the equation? So we have a 3 in the denominator on one side. We want to get rid of that. So we're going to multiply both sides of the equation by 3 using the multiplication property to get rid of the denominator. So that's your next step. We're able to do that because of the multiplication property. So then from there we have our arrow again. So once we do all that work, we're going to be left with y plus 2 equals 9. So again, we look at that. Why were we able to do that? Well, we're able to do that because of the substitution property, because we've kind of gotten rid of some stuff, and then 3 times 3 equals 9. So we can replace the 3 times 3 with 9. So that's our substitution property. Next up, we draw another arrow. And then we have y plus 2 equals 9. We can change it to y equals 7 because that's the subtraction property. We're going to subtract 2 from both sides, which would be our next step of the equation. So we've proven from y plus 2 divided by 3 equals 3, we've proven that y has to equal 7. Does that make sense? Okay, I hope that did. Because now we're going to move on to your first geometry proof. It's a fairly straightforward one. So our example is, given that Q is the midpoint of line segment PR, write a flow proof to show that line segment PQ is congruent to segment QR. Remember, when the bars are there, we're talking about the actual segment. When the bars aren't there, we're talking about the measurement. So that's the difference between using congruent or equals. So again, our first step, write our given and our prove. Given Q is the midpoint of segment PR, prove segment PQ is congruent to segment QR. So first step for our flow proof is write the box with our given statement and say that it's a given. Simple as that. Draw your arrow to move around. Next box we're going to do is PQ equals QR, because we're kind of given that the midpoint, we're told Q is the midpoint, and the definition of the midpoint, lost my train of thought there for a minute. The definition of the midpoint is that Q, being the midpoint of PR, makes PQ the measurement of PQ. Notice no bar. So the measurement of PQ is going to equal the measurement of QR. We draw our next step. Our next box is segment PQ is congruent to segment QR, because we know from the definition of a midpoint that these two measurements have to equal. Well, we know if two measurements of line segments equal, then the segments have to be congruent. So your answer and your reason there is for the definition of congruence. And we've done the first geometry proof in the class. Does that make sense? Okay. We talked about theorem. I mentioned theorems earlier. What this proof actually does is this proves what they call the midpoint theorem. And that's the theorem that says the midpoint of a segment creates congruent segments. So whenever we get to a point where we might need to use that theorem, we've proven the theorem. So now that we've proven the theorem, we're actually able to use it in another proof because we know that it's true, if that makes sense. Okay, so it's going to be your turn. We have their example here. I think there are a couple examples on your sheet, your notes. Take some time to kind of go through, create the flow proofs for them, and then just kind of give me kind of do them, and then we'll go over the answers. All right, so we got the proof. So our first step, again, as always, is to write down our givens. So our given C is between A and B, given that segment AC is congruent to CB. So those are the two given statements. We're told two things. C is between A and B, which is important because that means they're on the same line. And then AC is congruent to CB. Again, that's important. We're proving that it's a midpoint. So we're given our statement. We probably could have put that C is between A and B as well. I just forgot to put that in the box. So that's our given. PQ equals QR is our definition of congruence. If you have congruent line segments, then you have congruent measures. If you have congruent measures, we know then that Q is the midpoint. Or I'm sorry. I just realized that all my letters are all messed up. Sorry about that. So Q or C in this example then would be the midpoint because of the definition of the midpoint formula. So kind of wherever you see a P, think of A. Wherever you see a B, an R, think B, and then the proof works. Sorry about that. Didn't realize that as I was going through putting it together. Okay, the next one is the flow proof. If you guys kind of work on this, is a combination of using some geometry principles to then get to an algebra proof to do the algebra proof. So we're given that AB is congruent to BC. We have given a drawing 2, so we know that those two measurements are the same. We're trying to prove y equals 8. So if I know my measurement of AB equals my measurement of BC, then I know that 3y minus 9 has to equal 15. I'm just kind of thinking it through as we go through it. I know you've already kind of done the proof. So if that is true, this is what we have to do. 3y minus 9 equals 15. Then we're just going to kind of go through and solve that equation. So here's the proof all drawn out. You started with your given. AB equals BC from the definition of congruence. Then we're able to plug in, rather than AB, we can plug in 15 because that's kind of what the substitution is. We can substitute 15 for AB, 3y minus y for 3y minus 9 for BC. Now we go down. Flow proofs don't have to go from left to right all the time. You can kind of, the arrows pointing where you're going, everywhere you're moving, so we can go backwards. So we go from here down. We've done the addition property. We're adding 9 to both sides. Substitution property then, so we can get rid of the y on one side and the 20 becomes 24 on the other. We do the division property to get rid of the 3 in front of the y, because these are what we can do. So then we're left with 8 equals y, because the 8's on the left, which we then can flip to the symmetric property, so y equals 8. So we've gone through our proof, and we've proven that because AB is congruent to BC, we can prove that y has to equal 8. Does that make sense? This is the type of work that we're going to be able to do in our geometry proofs, that kind of once we've proven something works, so it becomes a theorem, then we are able to start using those algebraically to prove different angle measurements and things like that. So you'll see it gets to be a lot of good fun work, I think. Okay, paragraph proof. I'm just going to cover this today. I'm not really going to have you write one. I think there's one in the homework. I just wanted to show you what it looks like, because what it really is looking at the information that they want you to do, and then getting to the end of the point. I just realized that it doesn't have what we're trying to prove. What we're trying to prove here is that segment CA is equal to segment CB. I'm sorry that didn't end up there. For some reason it didn't come across in the notes. So we kind of look at what we have. We know that AE and DB are congruent. They tell us that. We're also told that C is the midpoint of segment AE and segment DB. So if you kind of think it through, we're talking about intersecting lines that are probably intersecting at point C if they're the midpoint of both. So from there now we kind of know what we're looking at, so we can kind of get through the proof, and then you're just going to write out like a segment paragraph. Like since we know C is the midpoint of AE and DB, then we can say that segment CA equals segment CE, which equals 1/2 of AE when you think of it, because it's midpoint, so each side's equal, so 1/2 of AE is going to equal CE and CA. We can say the same thing about the other side. Definition of midpoints is our reason. We're given that AE is congruent, so that then we know AE, the measurement of AE equals DB by definition of congruent segments. So then we know by the multiplication property that 1/2 AE is going to equal 1/2 of DB because they're congruent because of all the stuff. So we've kind of gone through and proven that CA equals CB. I know I kind of went through that quickly, but that's what you're looking at. How can I, as you're kind of explaining what's happening with the proof, that's what you're kind of writing down as your paragraph proof, plugging in your reasons as you go. So I hope that makes sense. Like I say, the paragraph proofs, it's there. You don't see them a lot in math. You see the flow proofs to kind of get people thinking about how to do the proofs. But then what we're going to do a lot of is what we're going to do tomorrow, and that's the 2-column geometric proof, kind of going line by line rather than box by box through the flow proof. But that's all it is. You take the flow proof and you can plug it into a 2-column proof, and it does the same thing, which is what you will kind of see tomorrow as we go through it. So if you have any questions, shoot me an email. The homework is on Google Classroom. It's doing some things where you're using postulates, proof statements true, and then there's a section on it of doing some flow proofs. And then there's a couple of higher level thinking problems where you got to kind of think of all this stuff together and try to come up with answers to some questions that way. So hope this was clear, and I will talk to everybody on Friday. Have a good night.